Now we're going to get to parametric equations and calculus. So we want to find, what we know is that if we have a smooth curve where the x is determined by the function f of t and the y value is determined by the function g of t, then the slope of c at the point x comma y is given by the derivative of dy dt over dx dt. The second derivative is d squared y over dx squared. And really this is d like dx squared. So we can rewrite this as the derivative with respect to x, so d dx of dy dx, which we can rewrite as the derivative with respect to t of dy dx over dx dt. All right, so let's go ahead and get started so you can see how this works. We have the function x is equal to 2 times the square root of t, and y is equal to 3t squared minus 2t, and we're going to find the first and the second derivative. So first off, I'm going to take the derivative with respect to t of x is equal to 2t to the 1/2 power, which gives me t to the negative 1/2. And then I'm going to take the derivative of y with respect to t, which is 6t minus 2. Now I can go ahead and find dy dx, which we know is dy over dt over dx dt. And so I get dy dt is 6t minus 2 over t to the negative 1/2. And then I'm going to go ahead and rewrite this as t to the 1/2 times 6t minus 2, which is 6. We're going to add the exponents to give me t to the 3/2 minus 2t to the 1/2. So that it would be my first derivative, dy dx. Our equation is still written in terms of t. Okay. So now we're going to find the second derivative, which is d squared y over dx squared, second derivative, which can be written as the derivative with respect to t of dy dx over dx dt, okay? And so I set this up as d dt of 6. I have dy dx, which is 6t to the 3/2 minus 2t to the 1/2 all over, and I'm just going to write dx dt for right now. Okay. So I take the derivative of 6t to the 3/2 minus 2t to the 1/2, which is going to give me, let's see, 18 over 2 is 9. T to the 1/2 minus 1t to the negative 1/2. To the 1/2. Yeah, okay, all over. And I'm going to substitute in my dx dt with my dx dt, which is t to the negative 1/2. We can rewrite that as t to the 1/2 times 9t to the 1/2 minus t to the negative 1/2. Multiply and add the exponents. So t to the 1, 9t to the 1 minus t to the 0, which is 1. 9t minus 1. So the second derivative with is equal to 9t minus 1. Okay, so I am going to show you how we get this. Okay, the second derivative at least. So what we do is we use implicit differentiation. Okay, so I'm going to start with my function, or the derivative d dx of dy dx is equal to d squared y over dx squared. Okay, so I'm taking the derivative with respect to x of dy dx, which is 6t to the 3 halves minus 2t to the 1 half. So let's take the derivative. I'm going to take the derivative, which is 9t to the 1 half, but because we're taking the derivative with respect to x and not with respect to t, I need to tack on my my chain or my implicit differentiation derivative. So the derivative of t with respect to x would be dt dx. And then we're going to take the derivative of negative 2t squared to the 1 half, which is minus t to the negative 1 half. Again, we're taking the derivative of t with respect to x. Now let's factor out my dt dx of 9t to the 1 half minus t to the negative 1 half. And I'm going to reciprocate the denominator to give me 9t to the 1 half minus t to the negative 1 half over dx dt. So what I did was I multiplied dx dt in the numerator, so that means I need to multiply by dx dt in the denominator to give me that term. I just moved it to the denominator but reciprocated it. So you can see here that when I do this, I end up with basically the same equation as I did up here. Okay. So this is how we get that dx dt in the denominator, or how we evaluate to give us the equation, or it's a proof for how we get the equation for the second derivative. Okay. I could keep going here, but I'm going to stop. All right. So find the slope and concavity of x equals the square root of t, and y is equal to the 1/4 t squared minus 1, where t is greater than or equal to 0 at the point 2, 3. Okay, so the point 2, 3, okay, there's a lot of variables here, so I'm just going to label this as x and y. Okay, so I want to find the slope and the concavity of the function. So I know that I need slope is first derivative, concavity is determined by the second derivative. So let's go ahead and figure out what our first and second derivative values are. But first, I'm going to write the derivative. So x is equal to t to the 1 half. So dx dt is 1 half t to the negative 1 half. And dy dt is equal to 1 half. 1 times 1, 2 times 1/4 is 1 half times t to the 1. All right, so that means that dy dx is equal to dy dt over dx dt. So I end up with 1 half t over 1 half t to the negative 1 half. So my 1 halves cancel, and then I'm going to add 1 plus negative 1 half, 1 minus negative 1 half, giving me t to the 3 halves. Okay, and so that's the derivative of dy dx, but I want to know the slope, particularly at the point 2, 3. Now the problem is that my function is written in terms of t. So I need to know when x is equal to 2, what does t equal? And I'm just going to plug in 2 for x to solve for t. Actually, I'll do it here. So x is equal to the square root of t. So that means that 2 times the square root of 2 is equal to the square root of t. So square both sides to give me t is equal to 4. So when x is equal to 2, that means that the time was 4 seconds, basically, or 4. So I need to evaluate dy dx, evaluated at t is equal to 4, which is 4 to the 3 halves, or the square root of 4 cubed. So 2 cubed is 8. All right, so the first derivative of the parametric function is 8. Okay, or the slope is 8. Put the slope at 2 comma 3 is 8. Okay, second derivative, we have dy d squared y over dx squared is equal to d dt of dy dx over dx dt. So I end up with the derivative of dy dx, which was t to the 3 halves over dx dt. Dx dt was 1/2 times t to the negative 1/2. Okay, so we're going to take the derivative with respect to time. So I end up with 3 halves t to the 1/2 over 1/2 t to the negative 1/2. Add my exponents to give us just plain t. So actually we're going to subtract them. So 1/2 minus negative 1/2 is 1. And then 3 halves over 1/2 is just 3. And then we need to evaluate the second derivative at t is equal to 4. So 3 times 4 gives us 12. And we can tell our concavity because the second derivative value is greater than 0. So the curve is concave up at 2 comma 3 because d squared y over dx squared is greater than 0. Okay, let's go ahead and check out the next one. Given the parametric equations, x is equal to 4 cosine t and y is equal to 3 sine t, write the equation of the tangent line to the curve at the point t is equal to 3 pi over 4. Okay, equation of the tangent line. So we need the point and the slope. So the point on the curve can be found by substituting in 3 pi over 4 into x, the equations x and y. So I'm going to start with my point. So x of 3 pi over 4 is equal to 4 times the cosine of 3 pi over 4. Okay, that's a 45-degree triangle, so we end up with 4 times the square root of 2 over 2, but in the second quadrant, so it's negative. This reduces to negative 2 root 2. So that's the x value of the point. The y value will be 3 sine of 3 pi over 4. So sine of 3 pi over 4 is, again, a 45-degree triangle. So we're going to end up with side lengths of root 2 over 2. And 3 pi sine is positive in the second quadrant where 3 pi over 4 is. So we end up with 3 root 2 over 2. So the point on the curve would be negative 2 square root 2, comma 3 root 2 over 2. Now we need the slope. Okay, we can find the slope by taking the first derivative at t is equal to 3 pi over 4. So dx dt is equal to negative 4 sine of t, and dy dt is equal to 3 times the cosine of t. So that means that the derivative dy dx is equal to 3 cosine of t over negative 4 sine of t. Okay, And then what I want to do is evaluate this derivative at t is equal to 3 pi over 4. So I end up with 3 times cosine of 3 pi over 4 over negative 4 sine of 3 pi over 4. And I get 3 times negative root 2 over negative 4 times root 2 over 2. And we just do a little simplifying. Okay, check this out. Boom, those cancel. So I get negative 3 over negative 4, which is 3 over 4. So the slope is 3/4. The point is negative 2 root 2 and comma 3 root 2 over 2. So the equation of the tangent line would be y minus 3 times the square root of 2 over 2 is equal to the slope, which is 3/4, times x plus 2 root 2. Yay! Next up is we're going to find the equation of the tangent to the equation of the line tangent to the curve given by 2 is equal to 3 cosine theta and y is equal to 3 plus 2 sine theta at the point negative 1, 3. This one is different because we're given a point. So I have x and y. First off, I'm going to verify that this point is on this curve, okay? So all I'm going to do is take my the x equation in the parametric equation, and I'm going to make sure I evaluate, I'm going to put in negative 1 in for my x value, because what should happen is that we end up with the same theta values, and if we don't, then we're going to have an issue, okay? So we have negative 1 is equal to 2 minus 3 times the cosine of theta, and then secondly, we want to use our y equation. Y is equal to 3 plus 2 sine theta, and we need to plug in 3 in for y from our ordered pair. And then let's make sure we get the same theta values, because if you don't, like I said, the point is not on the curve. Okay, so here we go. Subtract 2, we get negative 3 is equal to negative 3 cosine theta. So cosine theta is equal to 1. So cosine theta is equal to 1 at 0, 2 pi, and so on. All right, let's check out the y values, make sure they match up. So subtract 3, we get 0 is equal to 2 sine theta. So when sine theta is equal to 0, sine theta is equal to 0 at when theta is equal to 0 and 2 pi. Okay, so this point is on the curve. That's the first thing we got to do. Okay. Second, it says we need to find the equation of the tangent line. So I already know the point is on the curve. Now I just need the slope. So dy dt is equal to the derivative of 3 is 0, the derivative of 2 sine theta is 2 cosine theta. Okay, dx dt is equal to 0 minus, so actually the derivative of cosine theta is negative sine, so that negative is going to turn positive to give me 3 sine theta. Okay, so dy dx is equal to 2 cosine theta over 3 sine theta. And that is cosine, oh, well, let's just leave it like that. Okay, so we have dy dx evaluated at, and we need to know what theta value do I need to plug in. In other words, what theta value would give me an output of negative 1 comma 3. And the easiest one for me is just to plug in 0, okay, when theta is equal to 0. So I end up with 2 times the cosine of 0 over 3 times the sine of 0. And I remember that sine 0 is equal to 0. So I end up, well, cosine 0 is equal to 1. So 1 times 2 is 2, and 3 times sine 0 is 0. This is undefined. So we have a vertical tangent because the slope is undefined, like, like that. So we know that the equation goes through the point -1, 3. So the way we write that vertical line would just be x is equal to -1. Okay, couple more. Find all points of horizontal and vertical tangency given the parametric equations x is equal to t squared plus t and y is equal to t squared minus 3t plus 5. Okay, so I know that dy dx is the derivative and also gives me the slopes of my tangent lines. And dy dx as a parametric equation is dy dt over dx dt. So when dx dt is equal to 0, we have, because dx dt is in the denominator, we end up with a number divided by 0, which is undefined, which means that we have a vertical tangent line. Okay, dy dt is equal to 0 would give us 0 over some number, which just is equal to 0. So this means that you have a horizontal tangent. Okay, so let's go ahead and figure out what our, given our equations, I'm gonna write it over here. Dx dt is equal to t squared plus t. Oops, I just wrote the original. The derivative of t squared plus t would be 2t plus 1. And then dy dt is equal to 2t minus 3. Okay, to get the horizontal tangent, we want the numerator dy dt to equal 0. So all I'm going to do is take dy dt and set it equal to 0. I have an equation for dy dt. It's 2t minus 3. So I solve for t, and I get 2t is equal to 3. So t is equal to 3 halves. So when t is equal to 3 halves, we have a horizontal tangent, but it asked me for the points. So I know when the time is equal to 3 halves, we have a horizontal tangent, but I need to figure out the location. So x comma y. So I'm going to substitute x of 3 halves and y of 3 halves. Okay, so I get 3 halves squared plus 3 halves is equal to 15 over 4. And then for the y, 3 halves squared plus 3 halves times 3. Oops, I forgot. So it's 3 halves squared minus 3 times 3 halves plus 5. That is going to equate to 11 over 4. So at the point 15 over 4, comma 11 over 4, you have a horizontal tangent. Okay, vertical tangent, we set the denominator equal to 0. So dx dt is equal to 0. Okay, so we're trying to basically make the denominator equal to 0 so that the slope is undefined, kind of like the last example. So dx dt is equal to 2t plus 1. Subtract 1 from both sides, I get -1 is equal to 2t. So t is equal to -1/2. To get the point, I sub in x of -1/2, which is t squared, so -1/2 squared plus t, so -1/2. and that equals negative 1/4. And then y of negative 1/2 is negative 1/2 squared minus 3 times negative 1/2 plus 5, which gives us 27/4. So at the point negative 1/4 times 27/4, you have a vertical tangent line. Whoop-de-whoop. Okay, the last little bit for parametric equations is looking at the arc length of a parametric equation. So this is just the arc length of the curve, but we're defining the curve based off of the x movement and the y movement. Okay, so if you have a smooth curve given by c, where you have a parametric equation where defined by a third variable, what we can do is find the arc length by taking the integral from a to b of dx dt squared plus dy dt squared dt with respect to time. Okay, and usually these are a calculator question, so I am going to use my calculator to do this. We're going to set up the integral, and then we're going to find the length. So a particle moves along the smooth curve given by x is equal to t squared plus 1 and y is equal to 4t cubed minus 1. How far did the particle travel between t is equal to 0 and t is equal to 5? So I know that arc length of a parametric is defined by the arc length is equal to the integral from a to b of the square root of dx dt squared plus dy dt squared. It's like fancy Pythagorean theorem. Dt. Okay, so dx, the derivative of x with respect to time is 2t, and dy dt is equal to 12t. Okay. I'm going to substitute those in. Oh, 12t squared because it's a cube function. Okay, we're trying to find the arc length between 0 and 5. So my a is 0 and my b is 5. Okay, I end up with 2t squared plus 12t squared dt. Simplify this a little bit. Oops. Losing my brain here. 0 to 5 of 4t squared plus 144t to the 4th dt. And I typed that into my calculator to give me that s is about equal to 500.815. Okay, that was a lot, but we're done. Bye.